Hey, multivariable friends, how we doing? I did enjoy comments, so I did see that a few of you at least are watching some of the videos. I heard you liked my singing, so I'll keep that in mind. If I can think of any songs that relate to this lesson, I'll chime in. But if you've got any requests, I'm taking requests. We could make this karaoke hour. What do you think? That would be a lot of fun. Um, this is something that I think you've done before too in BC, integration with rational functions using partial fraction decomposition. And this first page of your notes, and I've already loaded the notes pages on there, so you've got it, is exhausting, I would say, to the nth degree. It boils down to this expression right here. You've got a polynomial over a polynomial, and especially when the denominator can factor. Okay? You could have a linear factor here plus a constant over a linear factor plus a constant over a linear factor plus another constant over a linear factor. I might want to elaborate at the end on the setup because I think it's important for you to be prepared for what you might anticipate. Even at lowly Westerville South High School back in 1983 is when I graduated, we did real problems like this. Not to say we walked uphill both ways to school and blah, blah, blah like an old man sounds like, but yeah, this is not a hard topic. So I want to extend it a little bit beyond what you might expect. So this first example is quite exhaustive there, and you can see all of that. I'll kind of show you how I walk through these when we get to some examples here that have some room to work. So you've got that, you should be good to go. Okay, so this is a good example here. Another one, and I call the Heaviside Layer, or the Heaviside method. Heaviside Layer reminds me of Cats. Anybody see that movie? Boy, we could have Cats karaoke. What do you think? Memory? No, we won't start that. But you're breaking things up into two factors and then finding a constant of this over that that's going to make your numerator. I'll show you an easier way. I understand what they're doing in this example, but let's try. In fact, let's go ahead and jump in this one and this one. We'll see those at work. Yeah, here we are. This first one, I can see that this will factor. So I always think right away, how is this one going to factor? So I've got the integral of x minus 4 over what? How does that x squared minus 6x plus 5 going to factor? Well, x minus 5, x minus 1, right? So I'm going to break that up into some integral of a over x minus 5 plus b over x minus 1. Okay? If you think about it, you couldn't use substitution, and this is why you need this. So sometimes the technique isn't hard, but why would we need to do this? Think about u. U is x squared minus 6x plus 5. My du would be 2x minus 6. 2x minus 6 and an x minus 4, no Quiero Taco Bell. Right? So that's not so good. So instead, I'm going to break it up into two fractions and hope that I could find a log of this and a log of that that would do that. Okay? So what we're saying is this. X minus 4 is the numerator of my first side, and I'm going to make this a comparable integral on the other side with that and that dx. A has x minus 5. It does not have the x minus 1 factor. Our x minus 4 on the other side did, so we're good. X minus 4 has everything it needs. What do you have? What do you need? So the a fraction needs the other one if we were to get a common denominator and add those up and set the numerators equal to each other. Plus, what does b need? The b fraction needs the rest of the other factor, x minus 5. Okay? And this is how I interpret the Heaviside method. Pick clever values, and they say it can be done short in your head. I mean, okay. But pick a clever value that's going to eliminate either a or b. I'm going to say let x equal 1. Well, how in the world did I come up with 1? If I plug in 1, doesn't that eliminate the a? Remember to plug that in for negative 4, though. On this side, x minus 4. This is not negative 4. 1 minus that is negative 3 equals 0. Plug in a 1 there, we get negative 4b. So solve that equation, we should get 3 over 4. Okay? Let x equals what would be another clever value? another clever value would be to eliminate the b function here, the b fraction, or the term here, because it's not really the b fraction. We solved for b's constant there. I could eliminate this term here, though, with x equals 5. 5 minus 4 is 1. A times 5 minus 1 is 4, isn't it? So b equals, and I see this every year. People say b equals 4. No, 1 equals 4b, so you're solving for b. I'm sorry, a. This is an a. This is an a, right? Because we eliminated the b already. So 4 times a equals 1/4. So that integral now becomes this. 1/4 over x minus 5 plus 3/4 over x minus 1 dx. If I write that one more time as 1/4 times the integral of 1 over x minus 5 dx plus 3/4 times the integral of 1 over x minus 1 dx. That's our favorite. That is log, isn't it? And a lot of these will turn into logs. 1/4 natural log absolute value of x minus 5 plus 3/4 natural log absolute value x minus 1 plus c. Okay? And it all depends on what's in your original numerator on what a and b is going to be. Okay? Turns out with this one, we needed both of those. This one is 2. Okay? So we'll do this one as practice 2. And then I'll kind of look at the next examples and see if we want to do those. I've also posted the answer keys to these notes, so if you want to see more worked out in the quite thorough, but I like what you need better. So this works for me. What would our setup be for this one? Let's just go ahead and do that one. Isn't this x minus 5 and x plus 4? X minus 5, x plus 4. So that equals 2 times the integral of x minus 5 x plus 4 dx. Well, I'm going to set that equal to, I'll just write it again just for good measure. And it doesn't matter who you call A or B, because as long as we keep it straight, we'll be good to go. Okay. Now, on the AP test, you were limited to, and that's why I'm going to turn the paper over and extend it to what I would need you to be able to do. My students remember this from last year, so this is something that a little bit of extension never hurt anybody here. But this is a linear factor that's not repeating, so the degree, and that's how log is going to work, right? The degree is going to be 1 degree lower, so this is x to the first power. The a is just a constant. That's x to the 0 power. A over x minus 5 plus b over x plus 4. What do you have when you need? 2 has everything it needs. A needs x plus 4. B needs x minus 5. What I'm doing is finding a common denominator. So for example, if you really need to see this, the b term needs x plus 4 over x plus 4. No, it doesn't. X minus 5. I misspoke. I wrote that on the right thing. X minus 5, x minus 5, right? So that red cancels, but that's what it needs. So what do you have? It needs x minus 5. It had x plus 4. So what do you have? What do you need? Set the numerators equal together once you get a common denominator. And I'm going to pick a clever value of x, negative 4. This side, 2 doesn't care. 2 equals 0. Negative 4, isn't that going to give us a ninth? So negative 9. B equals negative 2/9. Let x equal what? Negative 4? We already got that one. Positive 5. So we get 2, again, because this side doesn't depend. This side did, so make sure that you see that. Let's see, 2, 9, right? That's going to be 9a. So a equals positive 2/9. All right? So you should get the integral of a 2/9 times 1 over x minus 5 minus the integral, put our dx in here, minus the integral, 2/9 of the integral. We'll just put that b in there. That's 1 over x plus 4. And one thing you could write it out is 2/9 log x minus 5 minus 2/9 log x plus 4 plus c. Subtracting, I didn't do this one over here, but what if they, if it were a multiple choice question, they didn't have this? Could you use your log properties to condense this? Well, I hope I could factor out that. And if I'm subtracting logs, wouldn't you end up with 2/9? Factor that out of both of them, right? Natural log, absolute value of x minus 5 over x plus 4, because when we're subtracting logs, we divide the arguments. Okay? So there you've got that one, and that should be pretty straightforward too. Okay? Yeah, the next one is, I'm looking at it here now. I'll let you do that one. The work is all there. It would factor out, right, because you got 3 terms there, right? So we're going to have a x squared plus 12x plus 12, integral of that. What are our factors? Because I've got an x to the third. Well, if I factor out an x out of each of those, I'd have an x times x squared minus 4. Isn't that just going to be x minus 2, x plus 2? So for the first step of that, we'd have a over x plus b over x minus 2, in this case, plus c over x plus 2 in dx. But you're going to set aside the integral bit for a little bit and set clever values of x. I would pick 0, because what do you have, what do you need, right? You're going to have, well, let's do the first step. X squared plus 12x plus 12 equals, that has all 3 factors, so it's got everything it needs. A needs x minus 2 and x plus 2. It has x. Plus b, it needs x and x plus 2. Plus c, it needs x and x minus 2. And then go through the steps of setting x equal to 0 to eliminate this one and this one. So you'd have negative 4a equals 12, so a equals negative 3. So you can do it in your head. I write things down just because I don't want to make a lot of silly mistakes here. Let x equal to negative 2. Well, negative 2 here, here, and here. I'll let you do that math. Negative 2 would eliminate this term and this term, so we'd have negative 2 times negative 4, so negative 8c equals whatever that is, and solve for that one. And then the last one would be x equals positive 2. That's going to eliminate this one and this one. So it'd be 2 times 4, 8b equals whatever, plug in a 2 there, and you'd get that. I'll write down your answer so you can check that. It'd be negative 3 log absolute value of x plus 5 natural log x minus 2 minus 1 natural log of x plus 2 plus c. Okay? Now, with this one, and I'll let you look through the notes here, because with this one, hopefully you notice that the denominator is actually smaller. This is an improper integral, or improper fraction, because if the top is bigger, you need to break it up. So we're dividing x squared minus 6x plus 5 into our larger numerator x term. Okay? So hopefully you can do that. Practice that. You really should know how to do that. In fact, we probably should practice that. I'm looking at the time. We've got time to do this. I'll practice this division and let you do the partial fraction solving. How many times would you need to multiply this term to make it look like x to the third? Okay, because that's really what you're doing. I'm going to multiply that by x. So x times x squared is x to the third minus 6x squared plus 5x, right? And then here's our favorite part. I draw the line, I change the sign. So I'm going to change all those signs right there. X to the third minus x to the third, and that goes away. Subtract that properly, and you should get negative 3x squared. And subtract that properly, 24 minus 5 plus 19x. And then you can bring down your minus 17. Same idea. What am I multiplying to get that to match? Okay, because you know you're done after you get the final terms to match, right? So we've got that. Minus 3. So negative 3x squared plus 18x, right? And then minus 15. To draw the line and change the sign. 3x squared minus 3x squared, 0. 19 minus 18 is x. It's negative 17 plus 5 minus 2. Reason why I wanted to do this, some of you can do this division okay, but you have trouble with what that means. That means you're doing the integral of x minus 3, this stuff up here, plus our remainder x minus 2 over this giant hot mess. Well, it's not all that giant anymore. X squared minus 6x plus 5. Does that factor? Yes, you get to practice some partial fraction decomposition on that too. Okay, so that factors to be x minus 5, x minus 1. I think we did one similar to that, so you should be good. Then you got a dx. All right, so I'll let you finish that integral from there. Now, I want to show you some setups. So let's say we've got blah, blah, blah over x to, let's say, x squared times x plus 1. How many factors do you see? And some of you are going to say, well, I see 2. And I would counter and say you actually have 3 because x is a repeating factor. The setup for that is going to be a over x, that part we've got. This is what's different for some of us. Whenever it repeats, you're going to repeat it up to that term with another linear factor. Okay? Plus c, because that's a constant over a linear factor, x plus 1. And the reason why I said blah, blah, blah is depending on how interesting or complicated this, it might be a 2 and you might only have an a, or it might be an a and a c, or a b and a c, or an a and a b. It's too hard to predict what that would be. Since I'm just making these up, I'm not worrying about it. I'm worried about the setup. Then you'd set blah, blah, blah equals a times x, because it has 1x already, times x plus 1. B has x squared, so it only needs x plus 1. And C needs x squared, because it only needs the x terms and not the x plus 1. Okay? So I'll set it up again, just like I said. Blah, blah, blah equals A times, it has 1x, it needs another x, times x plus 1. What does B have? It has x squared, so it doesn't need x. It's already got it. Okay? But it needs x plus 1. Plus C, well, C has x plus 1. What does it need? It needs x squared. These are interesting because you actually would need to use a system of equations, and you might even need a calculator to solve a matrix problem with solving systems of equations. So that's why it's not taught anymore, because we don't do this anymore. But back in the day when I was a kid, uphill both ways and actually achieved, and you know, judging, not judging, judging, we had to do this. So you know, think about maybe you'll run into a college professor that's even older and meaner than me. Imagine that. So you might need this in a future life. Let's do another example here. Blah, 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 again, over x minus 2 squared, and I'm going to throw in another one here, x plus 1, x squared plus 1. Okay, this will be our last extension here. Do you agree that this is a linear factor?
Yeah.
Do you agree that there's 2 of them?
Yeah.
So we need 2 fractions, a over x minus 2 plus b over x minus 2 squared. Okay? Would you agree then, in fact, I probably shouldn't even write the integral because I'm not doing the integral, I'm just doing the partial fraction decomposition. Would you agree that this is not a factorable into linear factors, a quadratic factor that's not factorable, right? X squared plus 1 does not factor. So if I want the log pattern to work, it's u prime over u, right? So u prime is going to have an x term and maybe a constant. We don't know. Because again, we don't know what's in this blah, blah, blah in the numerator, the original problem. It could be something that some of your A's, B's, C's, and in this case we're going to have a D, are going to be required. So this needs to be a constant and an x term. So I'm going to call that cx plus d over x squared plus 1. Okay? It's always the degree, your A's, B's, whatever, your constants that you're decomposing this original fraction is always going to be 1 degree lower. So this is a linear term. That's a constant. The derivative of a linear term is a constant. The derivative, right, so u prime over u to get the log pattern to work for your integral. So I might have x squared plus 1. Now, yes, I agree. The derivative of 1 is 0. But d, depending on what this could be and how they all interact, you might need a cx plus d. If it was x squared plus 3x plus 8, I don't think that factors. You could see that you would need a cx plus d term in there for sure. Okay, again, just depending on how it would work out. So if it's a squared term that doesn't factor, you need a constant times x plus d. It should remind you of a function like a line. Okay, so you've got blah, blah, blah equals a. A has 1x minus 2. It needs another one. Plus b. It has both of them, so it doesn't need that, but it needs x squared plus 1. Plus cx plus d. Right? It has the x squared plus 1 term, but it doesn't have that x minus 2 squared term. Okay, and then you get to do, and you can imagine, you can see why this is not tested on the A/B test for high schoolers. I mean, yikes. We'd have people, I don't know, protesting that this was unfair and cruel and unusual. I think it's pretty cool, and now I feel like you're going to be ready for college, so yay. It was free, not to worry, included in the price of admission. There you go. So you got those. Don't worry if you see a problem like this in our class. It's just going to be the setup. So it would be just something like this. You'd stop right there. You'd stop right there if it was set up but do not integrate, blah, blah, blah. Set up so I can see that you listen to that lesson because that's a good one. That's a good one. Hopefully I can find questions in the question bank that are up to my standard of expectation. So, but in years past, I've asked these kinds of questions, and they've gone well. Or have they? I'll let you decide. You can do it. All right? So there's your lesson. Really gets us for 2 days, because you're going to have lesson tomorrow on this. I put up a quick 5-question quiz just to see that you've done some work with integration by parts. And what was the other topic that we did? I've already forgotten. Because integration by parts was the main topic on there. Let me scroll back in my notes here. Oh yeah, powers of the trig powers. So, sine squared, cosine, those kinds of problems. Powers of trigs. All right. So have a good one. That quiz is just a kind of a homework check kind of quiz to see that you're on track. You'll get this lesson tomorrow, Friday, and then day 11 will actually be practice. So that'll bring us into Monday for some practice. Hope everything's going well. Please let one of us know if you have some questions. If you got math questions, I'm certainly here to help you. Counselors are here, APs are here. A lot of folks are here on your side. So you just got to take the responsibility to do the work, and you can do it. All right. Have a great one. Talk to you soon.